Now let's start with breadth-first search, or BFS. It explores the graph one layer at a time, always visiting the nearest vertices first. Let's look at one idea shown at 3 levels of detail, side by side. The left column is the plain concept. The middle column is the pseudocode. The right column is the real C code. First step. We mark a vertex visited the moment we discover it. In pseudocode, visited at V becomes true. In C, visited at V becomes 1. Second step. We remember how far the vertex is from the source. Its distance is the parent's distance plus 1. So dist at V becomes dist at U plus 1. Third step. We remember who discovered it. We set parent at V to U, the vertex we came from. Fourth step. The vertex joins the back of the line. We enqueue it. Now the key point. Discovering a vertex and enqueuing it happen in the very same instant. That single timing choice is what the whole bug later in this chapter is about. Now the full BFS pseudocode, written in the CLRS style and zero-indexed. Q is a queue. Nil, read as null, marks a vertex with no parent. The first block sets up every vertex. For each vertex V, we mark visited at V as false. We set dist at V to infinity, and we set parent at V to null. Next, we set up the source. We mark visited at S as true. We set dist at S to 0, and we enqueue S. Notice we mark the source visited right as it enters the queue. Then the main loop runs while the queue is not empty. We dequeue a vertex U from the front. Then we look at each neighbor V in the adjacency list of U. Inside, we check one thing. If visited at V is false, we mark visited at V true. We set dist at V to dist at U plus 1. We set parent at V to U, and we enqueue V. Watch out for this one. You may want to mark a vertex visited when you dequeue it. That feels like the natural place. But before it ever reaches the front of the queue, every other neighbor enqueues it again, because it still looks unvisited to them. So mark it the instant you enqueue it. Then each vertex enters the queue exactly once. This is the chapter's main bug, and we come back to it in common mistakes. Your turn. Before the animation runs, try to predict the answer yourself. We run bfs from source 0 on this chapter's graph. These are the neighbor lists again. Remember, we scan each list in ascending order, smallest neighbor first. Here is the question. In what order are the 6 vertices dequeued? Pause the video and write down all 6 before you advance. Here is the answer. The order is 0, 1, 2, 3, 4, 5. Source 0 comes first. Then its neighbors 1 and 2 at distance 1. Then 3 and 4 at distance 2. Then 5 at distance 3. Nearest first, like a ripple spreading across a pond. Let's trace BFS from source 0, one dequeue at a time. First, the colors. White means a vertex is still undiscovered. Teal means it is in the queue, waiting for its turn. Red means we are dequeuing it right now and scanning its neighbors. Green means we are done with it. We start by putting the source, vertex 0, into the queue. Its distance is 0, since it is 0 steps from itself. The first table row shows the queue holds just 0, and the visit order so far is 0. Step 1. We dequeue vertex 0. It turns red, meaning it is the current vertex while we scan its neighbors 1 and 2. On the next step it turns green, done. Both 1 and 2 are new, so we discover them. Each gets distance 1 and parent 0, and we enqueue both. The new row shows the queue is now 1 and 2, and the visit order grew to 0, 1, 2. Step 2. We dequeue vertex 1, which turns red as the current vertex. Its neighbor 0 is already visited, so we skip it. Its other neighbor 3 is new. Its distance is dist at 1 plus 1, which is 2, and its parent is 1. The queue is now 2 and 3. Step 3. We dequeue vertex 2, which turns red as the current vertex. Its neighbor 3 is already discovered, so we skip it. Its neighbor 4 is new, with distance 2 and parent 2. The queue is now 3 and 4. Step 4. We dequeue vertex 3, which turns red as the current vertex. Its neighbors 1 and 2 are already visited, so we skip them. Its neighbor 5 is new, with distance 3 and parent 3. Look down the distance column so far, 0, 1, 1, 2, 2, 3. It only climbs, never falls. Step 5. We dequeue vertex 4. All of its neighbors are already visited, so it adds nothing new. The queue holds just 5 now. Step 6. We dequeue vertex 5 and it also adds nothing new. The queue is empty, so BFS is done. The visit order is 0, 1, 2, 3, 4, 5. Why was 5 never discovered twice? Because we marked it visited the moment it was enqueued, back at step 4. So when 4 looked at 5, it was already taken. Each vertex enters the queue exactly once. Here is a quick check on that trace. For the same graph in source 0, what is in the queue right after vertex 2 is dequeued? Pause and work it out. The answer is 3 and 4. Dequeuing 2 discovers its one new neighbor, 4. Vertex 3 was already discovered when 1 was dequeued, so it is not added a second time. That is the enqueue time mark doing its job. Now the real C for BFS, it matches the pseudocode line for line. The function is bfs. It takes the graph, the source vertex, and 2 output arrays, dist and parent, that it fills in. The queue is a plain array. 2 integers track it. QH is the head, the front of the line, and QT is the tail, the back. This is the visited array. It starts all 0, meaning nothing is discovered yet. This loop sets up every vertex. Dist at V becomes -1, our stand-in for infinity. And parent at V becomes null. Now the source. We set visited at source to 1. We mark it here as it enters the queue, not later. The comment says so explicitly. Dist at source is 0, because the source is 0 stepped from itself. And we enqueue the source. It goes into the queue at index QT, and then QT increases by 1. The draining loop is on the next slide. The main loop runs while QH is less than QT. That simply means the queue still has vertices waiting. We dequeue the oldest frontier vertex into U, we read Q at index QH. Then QH increases by 1. This loop scans U's neighbors. It walks the adjacency list until it hits the null marker at the end. We copy the current neighbor into V, so the rest of the block reads more easily. This is the key test. If V is not yet visited, we do the work inside. We set visited at V to 1 right here, before V ever waits in the queue. This one line's placement is the heart of the whole chapter. Dist at V becomes dist at U plus 1. The new vertex is 1 step further out than the one that found it. Parent at V becomes U, recording who discovered V. And finally, we enqueue V. The cost of BFS is big O of V plus. Every vertex is dequeued once, and every edge is examined once from each endpoint it touches. Let's run the program and read its output. It prints 1 line per vertex. The three columns are vertex, distance, and parent. Vertex 0 has distance 0 and parent -1 because it is the source with no parent. Vertices 1 and 2 have distance 1, 3 and 4 have distance 2, and 5 has distance 3. The output is deterministic and it prints values and indices only, never raw addresses. Watch out for one belief. You may think BFS always finds the shortest path. That is only true when every edge counts as one step. That is, an unweighted graph. Once edges carry weights, fewest edges is not the same as lowest cost. For that you need Dijkstra's algorithm in Chapter 16.